Hey guys, so yeah, like I told you, this portion of the semester I'm gonna come in strong with these videos, and we'll see how well they help you guys retain the material. So we're gonna look at more applications of Newton's laws. All right, let's get to it. So anyway, before we get into it, before we get into it, I want to briefly talk about a problem-solving strategy that we've developed so far. All right. So the first question is make your coordinate system. All right. So you need when you have a Newton's law problem, make a coordinate system. Tell me where positive y and positive x is going. And normally you want the positive direction to be the direction in which the object is moving, but sometimes not. But you just have to consider that. All right. After that, make your free body diagram. All right. And by the way, how to draw a free body diagram, you need to have the tail of your vector on the dot, like on the object, like if this is an object, my object, all right? How to draw a free body diagram. You need to have the tail of your vector at the object and the tip in the direction of where the object is going. All right. So if it's like being launched somewhere at an acceleration, and this will be my free body diagram. All right. So yeah, I'm going to say only forces go here. All right. Velocity is not a force. I don't want to see velocity on your free body diagrams. All right. Velocity is not a force. Yeah. And an important thing also is vectors are drawn from the tip at the object. All right, so object is here, the object we're analyzing, and then the tip goes, and then the tail points in the direction. All right, it's never, though this is correct, it's never like this. The tail should not point at the object. This is wrong. All right, so yeah. So anyway, after we draw our free body diagrams, we identify the forces in the x and y directions. All right. So in short, we calculate the sum of net forces in each direction. So the x. So like if I have my free body diagram has forces in my x direction, there will be that'll be force 1, force 2, and so on, like maybe friction or weight, the x component of weight, x component of tension or something. And yeah, and then so the y direction, same thing. We have let's say the y component of weight, normal force, and so on. Those are some common forces you see in the y direction. So now after we do that, after we get all our forces, we apply the Newton 2 condition. All right, the Newton 2 condition. This just means, so you see the Newton 2 tells us that the sum of forces, the net force, the total net force, the sum of forces here is the net force. So the net force, all right, is equal to ma. All right, so we just plug in ma for f of x, so that's and then may for f of y. All right, and it looks like this. This is the same thing. These are equivalent, you see? These are equivalent, but plugging in for Newton 2 helps us solve for acceleration. Because in the end, we want to find like the acceleration and objects going at and so on. And then, yeah, we'd normally do some algebra here and there. But yeah, so this is what we've been doing thus far. This is what we've done, all right, in class so far. So just keep in mind this whole process, all right? So now, today, we're going to learn how to attack specific types of problems using Newton's laws, all right? Today, we're going to learn about equilibrium problems. What color should I use today? Let's see, I like this purple, all right? So, what is an equilibrium problem? Yeah, you might be curious. What is an equilibrium problem? What's Mr. Makelele talking about? So, this is a problem where an object is in equilibrium. Yeah, I know this is not a complete definition, but hold on, just let me do my thing. So, a problem where an object is in equilibrium. How do we know an object is in equilibrium? How do we know an object is in equilibrium? All right? When the net forces in the horizontal and vertical directions each sum to 0. All right? So what this means basically is that the sum of forces in the x direction is going to be 0, and the sum of forces in the y direction is going is going to be 0. This makes our algebra a lot easier. All right? And also, because the force is 0 in the x and y direction, it also means that, all right, it also means our object is not accelerating in either direction. All right? So our object is not accelerating in either direction. So in the y direction, the vertical direction, f of y is equal to 0. In the x direction, f of x, I'm talking about them like that, functions. Fy, the force in the y direction will be 0, and the x direction, the force in the x direction will be 0 as well. All right? So, yeah, that's basically the state of equilibrium. Yeah, and there's no acceleration on the object at all. All right, I just want you to get that. So now, how do we know an object is in equilibrium? Oh, we just answered that. Sorry, I wrote notes earlier and I'm just repeating my notes. All right, so we have two kinds of equilibrium. We have the static equilibrium, all right? So this is basically when an object is at rest. All right? An object is at rest. The static equilibrium. And then number 2, we have the dynamic equilibrium. All right? This is when an object is undergoing constant velocity. All right? If the velocity is constant, we are not accelerating. All right? I hope at least we can believe that from our kinematics studies. Yes? Yeah. So, these are the two kinds of equilibrium. So when an object is at rest, we say it's in static equilibrium. When an object is moving at a constant velocity, we say it's in a dynamic equilibrium. All right, let's solve some problems now. Yeah, this is physics. You just understand the theory, and then you solve some problems. Okay, so when is an object in static equilibrium? I'm just read this statement. When is an object in static equilibrium? Well, okay, when it's at rest. Yeah. So arrow is back. Arrow's made a comeback. So consider arrow. Here's our problem. Yeah, this is our problem. Consider arrow lying on the ground. Arrow's mass is 50 kg. What is the normal force on arrow? All right. Interesting problem. Okay. So this is my scenario. Oops. My scenario. Arrow. That's arrow. He's on a surface. All right. I don't know. I don't like he's floating right now, but let's see if I can move him a little bit. Yes. That's Earl. What forces are so now? Okay? So this is my situation. All right. Earl's on the surface. Step one, coordinate system. Okay. So my positive y will be up there. My positive x will be down there. Will be to my right hand side. What forces are acting on Earl? Well, the gravitational force for sure is acting on Earl. Oh wait, but we see Earl also on the surface. So yeah, Earl's weight is acting on Earl. Oh, we see Earl is also on the surface. So the normal force is acting on Earl as well. Interesting. Okay. So now, okay. So what's the next step in our scenario? I can't remember. Let me move back. The next step. So we have a free body diagram technically. It's kind of so. Actually, we don't have a free body diagram yet, but it's basically on our drawing. But just for clarity's sake, I'm gonna put the free body diagram right here. Our free body diagram. There's Earl. See, vector from object. The tails of the object. Sorry, the tails of the object, and the tip is pointing over there. And the normal force is up there. All right. So there's our free body diagram. So now the next step from here is to calculate the sum of forces in the x direction and the y direction. All right. So let's see. I got step one. Let me see if I can just make this clearer. Step two is step one. Step two. Then step three. All right. So we want to calculate the sum of forces in the x direction and the y direction. All right. So sum of forces in the x direction, sum of forces in the y direction. Yeah. Okay. So what's the sum of forces in the x direction? Well, we're at rest. We aren't moving out low in the x direction. We're at rest. So that's 0. All right. There's nothing pushing it. Remember, force is a push or pull. There's nothing pushing it to the left or to the right. All right. Now, what about the y direction? Well, so in the positive y direction, we have the normal force, but I see my weight is pointing down, opposite to the. I see okay. Let's ignore that red line for now. I see my weight is pointing down, opposite to the direction of positive y up on my coordinate system. So it's going to be negative y. But now remember, my object is at rest, so it's in equilibrium. All right. Object at rest, comma. So equilibrium condition applies. Yeah, so that means f of y is going to be equal to 0. All right? And f of x should be equal to 0, but we already know that from the net forces as well. So f of y So f of y equals equal to 0. All right, so now our equation, if I say this is equation 1 and equation 2 looks like 0 is equal to the normal force minus the weight. Okay, and we want to, the question is, what's the normal force on L? So we can algebraically manipulate this and just say, like I add the weight on both sides. I say the weight is going to be equal to the normal force. All right. Now, what's the weight? Our weight is mg, right? Weight is mg. G is equal to the normal force. And what's our mass? Our mass is 50. What's G? G is 9.8. It's going to be the normal force. All right. That's a put it in the calculator, and there's your answer. I don't really like, the physics ended here. This like, if you did this question in an exam and you just reached there, I don't mind. I don't mind if you make a mistake in the math calculation, like, so long as you derive the correct formula. All right. So yeah, this is how equilibrium problems make life easy for us. You see, like, if you go back to our steps, after we apply the Newton 2 condition and solve, here we can simply just say f of x is equal to 0 and f of y is equal to 0, because we know the object is in equilibrium. All right? I hope that's clear. Anyway, let me not leave this unsettled, because I know how much you guys like numbers. So 50, hold on, 50 times 9.8. Okay, so that's what? 490 Newton. So 490 Newtons, yeah? So, yeah, that's our normal force. We found it. Woohoo! And we use the same exact step, except that, we use the same exact steps, barring the fact that we had to substitute in 0 for our net forces for f of x and f of y. All right? So f of x, so yeah, I hope this brought some clarity to that. Let's do one more. Let's do one more dynamic. Hold on, there's a lot going on in my notes right now. Let's do one more static equilibrium problem. All right? So we have 3 ropes on a ring. Yeah? We have 3 ropes. And they're tied to a small light ring. Let's say this is Earl's wedding ring. Yeah, Earl's a penguin and he's married and has disposable fingers. So yeah, anyway, 2 ropes, rope 1 and rope 2 are anchored to walls at right angles, and the third rope as shown. So this is the third rope, right? Rope 3. What are the magnitudes of tensions in the 2 ropes? So we want to know the magnitude of tension in the 2 ropes, in rope 1 and rope 2. All right? So we know the magnitude of tension in rope 3, all right? So I can say rope 3, the tension is 100 newtons. All right. So so let me begin this problem, yeah? Step 1, let me change the color a little bit. Hope this doesn't look disorganized, but these 2 are the same color. Let's say orange, yeah? This is step 1, coordinate system. All right, so I guess I'm gonna just stick with the regular one here. My positive y, my positive x. Yeah, nice. So now we have an interesting. So hold on, let's do our free body diagram before we go there. All right, step 2, free body diagram. All right, So we have T1 tension pointing towards the wall upwards, and then there's a 90-degree angle. Why did this curve? We have a 90-degree angle. Oh my god. I'm really trying, guys. I'm really trying. Okay, that's good enough. And we're in a 90-degree angle going to tension 2. And then we have a 30-degree angle here going towards tension 3. All right? 30 degrees. So, from this point now, we can calculate the magnitude of forces. All right? This is something we need to do. Anyway, so step 3. Step 3. Calculate the sum of forces in the x and y direction. All right? So, in the x direction, what do we have? Well, you see, every time of a vector at an angle, guys, always divide it into its components. All right? So, we have, let's see, we have T2. That's minus T2 because it's pointing opposite to the positive side. And then we also have, let's see, the x component, positive T3 x. So the x component of the T3 vector. All right? And then from there, so I think that's it for the x direction. For the y direction, we have the y component of the T3 vector. It's going to be minus T3y because it's pointing down. It's negative because it's pointing down. Plus T1. T1 is pointing up. All right? Okay. So now for equilibrium problems, because we see our ring is not moving. It's static. It's really not moving. It's tied to the ropes and it's not moving. So we can apply our equilibrium condition. Apply equilibrium condition. And so we're saying f of x is equal to 0, f of y is equal to 0. Yeah? So now, what do our equations look like now? We have, let's see, step, okay, no, let's just keep that. What do our equations look like? So, zero is going to be equal to minus T2 plus T3x. And then 0 is going to be equal to minus T3 minus T3y minus T1. All right, so now how do we find these components? We break it down to its component vectors. All right? We break down T3 into its components. All right? So if I look at my T3 triangle here, yeah, I can redraw my triangle like this. All right? I can easily redraw this because this is a diagonal, so I know T3 is my hypotenuse right there. And then the angle it makes with the horizontal is 30 degrees. And then we have a T3x over there. And then vertically, right here, we have a T3y. All right? So then what's cos theta then? All right? Cos theta course, I've got my car. Adjacent is going to be T3x. Oh, we get x. I always like getting my x component of my cosine for some reason. I don't know why I'm attached to that, but yeah. T3x is going to be equal to T3. So my hypotenuse is T3. So T3x is going to be equal to T3 cosine theta. All right. Now what about T? What about T3y? Hold on. So I'm pretty sure that one I need my sine theta. So sine theta gonna be equal to, so that's so my opposite is going to be T3y, opposite to the angle, T3y over T3. And so if we cross multiply, it's gonna be T3y equal to T3 times sine theta. All right. So we've solved for our equation. We know T3x and T3y. All right. We know T3x and T3y. All right. Let me just make a line here so we don't have any confusion. So now I can plug in T3x and T3y. All right. So I'm gonna plug. So let's see. I'm gonna plug in vector values. All right, so 0 is going to be equal to, let's see, minus T2 plus, see, T3x is T3 cos theta. And then 0 is going to be, T3y is going to be, let's see, minus T3 sine theta minus T1. All right. All right, we're getting very close to solving this problem, guys. So now all we need to do is move. So the magnitudes you want to find out are, let's see, the magnitudes you want to find out are those of T2 and T1. So let's get T2 and T1 on one side of the equation. All right, if I say this is equation 1, this is my equation 2. So let me manipulate equation 1. So equation 1 is going to be, hold on. My equation 1 here, we'll have, I'm going to move my T2 across the equal sign. With T2 going to be equal to T3 cos theta. All right, that's this equation. And if I move my T1 again across the equal sign, T1 is going to be equal to minus T3 sine theta. All right, boom. We solved the problem. All right, we have the correct formula. The physics is done. The physics is finished. Now it's just math, all right? If we look at our line there, we know T3 has a magnitude of 100 newtons, and theta is 30 degrees Celsius. So, Celsius, that's funny. I'm sorry, guys. Anyway, just plug that into a calculator, and boom, there are your magnitudes. So, physics is done here. Physics is finished. Now math. All right? And I myself, I'm not gonna do something for you guys. I'm sorry, but you can do it yourselves and see what you like. But if you can get to this point where you have the magnitude of T2 and T1, with me, I'll give you full credit. All right? So, yeah. There's your... I mean, it kind of makes sense, you know. So, let's see. Because these are basically projections. So, T1 and T2 are basically projections of the tension. Sorry, of T3. You know. So, T. This is where T. This is where T3. This is where T3y is, and this is where T3x is. All right? So you see, we kind of have that kind of symmetric lineup a little bit, and that really helps us solve this problem. And also the fact that we're in equilibrium again. Being in equilibrium made this problem very easy. If we're in equilibrium, we had to equal our sum of forces to ma, and there'll be an acceleration, and yeah. So that's static equilibrium, guys.